All right. It's a great pleasure to welcome you all to third day of this Group Theory Sangam conference. Our first speaker today is Dr. Sushil Bhunia. He did his PhD at IISER Pune and he is presently at IISER Mohali. So Sushil will speak on twisted conjugacy in big mapping class groups, as you can already see on the slides. Sushil, over to you.
Okay. So first of all, thank you very much, Sripat, for the introduction, and as well as thank you all the organizer of this conference, Group Theory Sangam. So, so I'll be speaking about some twisted conjugacy, about a particular class of groups. It's called big mapping class group. So the idea is I'll first define what twisted conjugacy is, and then I'll define big mapping class group, and then few results, not all. So that is the idea of this talk. Well, so first define what twisted conjugacy is. Already in this group theory Sangam, Anirban gave a talk on this twisted conjugacy, and also in Mahendra's talk there was some twisted conjugacy was there. Okay, so you fix a automorphism of a group G. So G could be any group, and fix an automorphism. And then you define an equivalence relation with respect to this automorphism. Let's say phi is the automorphism. And then you define this relation that two elements are related if they satisfies this equation, like y equal to gx phi g. So as you can see, this is a generalization of a usual conjugacy relation, because if I take phi to be identity, then this is the usual conjugacy. So then one can check that this relation on G is an equivalence relation, and the equivalence classes are called the phi-twisted conjugacy classes. In fact, also in Redemaster Nielsen fixed point theory, they use this phi-twisted conjugacy as Redemaster classes. So yeah, so in the fixed point theory, they have uh, some motivation to study this Redemaster class, and the number is called the sometimes Redemaster number. So that brings us to the following definition. So now, once you have twisted conjugacy, then you can study analogous properties of the conjugacy. But for this talk, I'll be concentrate only one property that is called R infinity property. So what is this? It says that a group is said to have the R infinity property if the number of phi twisted conjugacy classes is infinite for every automorphism. So a group to have the R infinity property, first of all, it has to have infinitely many conjugacy classes, because for identity. So that's the notation for R phi. R phi is because stands for this Redemaster. And if it is identity, then it's as usual, this is the number of conjugacy classes of the group. So this is the property I'll be talking about, this R infinity property of the group. So let's see some examples which satisfies this R infinity property. So if you take free group on at least two generators, special linear group over Z, Q, and R, they will satisfy this R infinity property, and so on. So you define a property and then satisfies all the groups, so it's now good. So there are also counter examples, like non-examples. There are a lot of groups, in fact, which does not satisfy this property. So for example, if you take a free abelian group, infinite free group also doesn't satisfy this property. And you take the upper triangular matrices, which also doesn't satisfy this R infinity property. So, okay. So let's see a particular example. So if you take Z, for example, we know that there are only two automorphisms. One is identity, one is minus identity. So we know that the identity gives you infinitely many conjugacy classes. So good. But for minus identity, they form exactly two classes, one for even integer, one for the odd integer. So Z doesn't satisfy this property. In fact, Zn kind of same proof, sort of proof will work. So, okay. So, but why should study this kind of properties? So this is the list. I am not going to go through this list. Those lists is shows that there are a lot of activities going on to study this property of being R infinity satisfied by your favorite class of groups or a group, whatever. So, so there are like two sides. So one is like algebraically there are so many results, and another side there are so many results on the geometric side. So for this talk, I'll be interested in this geometric side. So for example, hyperbolic groups and relatively hyperbolic groups, they do satisfies the R infinity property. And then this is a hierarchy. Like if it is hyperbolic, then it is already relatively hyperbolic, and this containment is proper. And then there is another big class which encompasses both the hyperbolic as well as relatively hyperbolic groups, which is acylindrically hyperbolic group. So one would like to understand the R infinity property of this kind of group, that whether a acylindrical hyperbolic group satisfies this R infinity property. So the answer is still open. I don't know. No one knows what is the for this acylindrical hyperbolic group. So if you don't know for a class of groups, so at least one should look at some examples which belongs to this class of acylindrical hyperbolic group. So that brings us to this mapping class group, which is acylindrically hyperbolic group, but not hyperbolic or relatively hyperbolic. So in order to define this mapping class group, we have to, so because this mapping class group is actually attached to some surface. So first just let's look at some surfaces before just introducing formally what is this mapping class group is. So a surface, by a surface, I mean a two-dimensional manifold which is connected and orientable and boundaryless. So for simplicity, I assume boundaryless, but can be defined this mapping class group also with the boundary. And then this is a standard definition. The surface is called finite type if the fundamental group of the surface is finitely generated. If the fundamental group is not finitely generated, then the surface is called infinite type. So usually in the topology, we see this finite type of surfaces. So it has been, in fact, classified using this genus. Genus is some number attached to each natural number. So for each natural number, you'll get a one closed surface. So there are like countably many surfaces. In fact, we know the exact, like how does it look like, the fundamental group given by this generator and relation. So it's clearly finitely generated. So it's a finite type of surface, but other surfaces are infinite type. In fact, if the surface is infinite type, then the fundamental group is always free group on countably many generators. So, so as you can see that the finite type surfaces kind of like topologically still good, because if two surfaces are not homeomorphic, two fundamental group of two surfaces are not isomorphic, then the surfaces may not be, and they are not homeomorphic at all. But on the contrary, for infinite type surfaces, all the fundamental groups are free group on countably many generators. So therefore, topologically, it's little bit, let's say, topologically bad. And then, so for example, for finite type surface, we know that this each natural number will give you one surface, at least for closed one. And then if you allow punctures, then there are complete classification. As well as for infinite type surfaces, there are also classification. So I won't go into the detail of the classification of these surfaces up to homeomorphism, but I'll give you some example which will say something about these classifications. So from now on, mostly I'll be talking about infinite type surfaces, except one slide. Okay. So these are some examples. So we know if genus is 0 for finite type surface, this is just a sphere. But on the contrary, if the surface is of infinite type and genus 0, then there are uncountably many such surfaces. So for example, in this slide, I gave two examples. One is like R2 minus a Cantor set, which is same as sphere minus Cantor set with removing the north pole. And the another surface is a fluid surface. It looks like a fluid infinitely going on. The fluids thing is like the punctures. Okay. So if you take your favorite G-genus surface and remove a Cantor set, so it's always infinite type surface. So this we will mean like the Cantor set, because Cantor set is totally disconnected, just to say that it's totally disconnected. Okay. So now if genus is infinite, there are so many surfaces. For example, this Loch Ness monster, this is infinitely going, this genus, there are so many handles, infinitely many genus. And this is going one end. You have a second one is the Jacob ladder surface, two ends, two different ends, and but the infinite genus. So then you can see the pattern, like two ends, three ends, four ends, and so on. So in this way, you can generate countably many surfaces of infinite genus and ends. Okay, so this is kind of this ends, genus, and uh, will almost determine the infinite type surface up to homeomorphism. Okay. So now, having said that, I can define what a mapping class group is. So now you have a surface. I am assuming the surface has no boundary. So now look at the homeomorphism of the surface. So now it's a groove in its own right by composition, and then you mod out by some relation. So then elements of the mapping class group is nothing but an equivalence class. So what it says that two homeomorphism belongs to the same class if they are homotopic to each other. Homotopy or isotopy is same in the surface situations. And since I also assume that the surface is orientation preserving, so therefore you can also talk about a finite two index subgroup, in fact, just orientation preserving one. So this is an index two sub. So for example, if you take a torus, okay, so it's a bad notation. Torus T2 here, I mean the usual torus, like the sigma one in the earlier notation. So if you look at the mapping class group of the torus, it's GL to Z. And if you look at the orientation preserving one, it will SL to Z. So it's very concrete. For a torus, the mapping class group is very nice. And this is the only example I know, like the clearly. And yeah, no other concrete examples I don't. And in fact, this is not a surprising fact that if you take any G-genus surface, the mapping class group is always finally generated. So topologically, it's a discrete topological space. So this is just a natural. Whereas if you take an infinite type surface, it is always uncountable, homeomorphic to this bare space. So that's why this name is coined by Danny Caligari, that the mapping class group is called a big mapping class group if the surface is of infinite type. Bigness is lies here because of this uncountableness. Okay. So that's all about the mapping class group. Now I want to study this property of R infinity for this mapping class group. So now first look at the finite type setup. So this is a result that the mapping class group satisfies this property, the being R infinity, if and only if it's not a sphere. And the proof the OS this proof, I'll just say just a couple of lines that so the mapping class group acts on the homology by the automorphisms, and then it induce, and then it will sit inside some GL2ZZ, but again there is some intersection form like the symplectic form, it will preserve. So this is a surjective map to the symplectic group, and the kernel is something called Torelli group, whatever it is, some kernel. So now you have a nice short exact sequence. It may not split. Yeah, it's not necessary. And then they prove first that this right hand side SP symplectic group satisfies the R infinity property, kind of inductively proving that SP2, which is SL to Z, has the R infinity property. And then they prove that the kernel is characteristic. So therefore, there is a general, if you have a short exact sequence, the right hand side is satisfies the R infinity property. Then the middle one also will satisfy the R infinity property, provided the left hand side is a characteristic sub. So this is sort of like the idea to go about this. So this is the linear part will says that something. So in this short exact sequence, usually in the mapping class group, they say this symplectic is the linear part, and this is the kernel is non-trivial, like the non-linear part in some sense. So the linear part says the R infinity property about the mapping class group. So then a natural question is, how about big mapping class group? So in order to understand this R infinity property, one should have know like what is the automorphism group. So once you know the automorphism group, and then you can say something about the R infinity property. So okay, so once you ask the question, then there is an answer. Yeah, so that's why I asked the question. So the answer is due to Weber, Dowdell, and Ruffy. Recently, they proved that the automorphism is exactly the all the mapping class group. Meaning, so if you spell it out, this theorem, this says that if you choose any automorphism, then this can be given by conjugation. But the conjugating element need not be coming from the orientation preserving one. It could be orientation reversing as well. So this boils down to these two things. So if you look at the all the mappings, like the mapping class group, you don't say only orientation preserving, you allow both the homeomorphism, orientation preserving, then the outer automorphism is trivial because this is given by just conjugation. Whereas for the orientation preserving one, you will get one outer class given by this orientation reversing homeomorphism. So now we have to study that the inner automorphism and the one outer automorphism to study the R infinity property using this theorem. Okay. So this is a basic lemma. So first I will talk about inner automorphism. So it says that if you compose any automorphism by inner automorphism, the number, this number is the number of twisted class. This is ready master number, is same for a automorphism and if you twist it by some inner automorphism. So in particular, if you put pi, this phi, the automorphism to be identity, then for inner automorphism, this number is same as the number of conjugacy classes. So which is good. So now, but how to prove that the number of conjugacy classes for this type of group is infinite? This is not clear. So for example, if you have some linear group, then we can use some trick like the trace. If the trace set is infinite, then the number of conjugacy classes is infinite in the kind of linear setup. So in analogy, in geometric group theory, there is something called, this is the standard technique in geometric group theory, is called translation length. So for me, it seems like analogous to the trace in the linear group. So what is this? So suppose you have a group G, which acts on a metric space, but the action is by isometries. And then for each element, you define this limit. So you look at G to the power n dot x, this is the action, isometric action, and you compare the distance and they divide it by n and take the limit. So, so this is the translation length for each element of the group. So now the natural question is, how about limit exists? Yes, limit exists. And the next question is, you define for some fixed point x. Yeah, this is doesn't depend on the point x. If you change it some other point, this definition is like well defined. And the third thing, which is we used basically, that it is conjugacy invariant. So it is like easy proof. Okay, let me go through the proof, just simple proof. So if you look at the translation length of this conjugation, this is by definition, the second line. And now we know that the action is by isometry. So you can pull this out by H inverse. So you got this. So now the second point says it doesn't depend on the point. So H inverse x is my new x. So this is the translation length. So therefore, this translation length preserves the conjugacy. So in order to prove that there are infinitely many conjugacy classes of a group, you find out a suitable space on which the group acts, and you prove that there are infinitely many translation length, a distinct translation length. And the third property says that you apply G several times and look at this translation length. This is just multiplied by that. Okay, so this is like similar proof. So as a corollary of this description of this translation length, we got that if you have a group act isometrically, and translation length is always greater or equal to 0. But if you find one element whose translation length is positive, then the number of conjugacy classes is infinite. So the proof, so first of all, translation length positive implies the element has to have infinite order. Second thing, you look at the sequence, G, G square, GQ, and so on. And then the fourth property says that if this is conjugate, G and G square, then translate like 2 will be 1. So it is a contradiction. So clearly you gave a representative like G, G square, GQ. Those are the infinitely many conjugacy classes of G. So this we have used to say that it has infinitely many conjugacy classes. Okay, so next I'll define the another tool that has been used, and I'll state one result regarding this and idea of the proof. So this is popularly known as BIRMAN exact sequence. So you have a surfaces. This makes sense for finite, infinite, both the type of surface. So for finite type surface, the proof is been there. Also infinite type surface, the same proof will work. So you fix some point and you look at any homeomorphism. So I'm like doing it for infinite, only orientation preserving one, because if it is not, if the group of the mapping class group is containing all the orientation preserving as well as reversing, then we know that conjugacy classes are enough to say that the group has infinite R infinity property or not. Okay, so what is this? So this is the fiber bundle. So forget about what is this fiber bundle or whatever. So you take a orientation preserving homomorphism and then evaluate it at that point X. So then the fiber is all the homeomorphism which fix that point. So got a kind of this sequence. And then in topology, if you see this kind of sequence, you immediately apply homotopy long exact sequence. And then I am just looking at the relevant part of the sequence. So you apply the pi1, so pi n functor on this sequence, you'll get a homotopy long exact sequence in the homotopy class. So now look at this. So since the surface is connected, so the pi 0 will go, and then there is a result that pi 1 of this homeomorphism group is trivial. Like this is in fact contractible, and not contractible. Sorry. So this is homotopy equivalent to identity. Is connected component. So then you got a sequence, a long exact sequence, and then two ends is 0, which is good. So just let's rewrite this sequence. So we got this sequence using this technique of homotopy long exact. But what is this? So pi 0 is nothing but the mapping class group. And so that is by definition. So this is topology. So I forgot to mention that the topology is a compact open topology. So you have a surface, and the topology is the, like, in general function space, the topology is compact open topology. With respect to that topology, look at how many components are there, and in the definition, this is like same as the mapping class group. So you got a short exact sequence of the mapping class group, where the middle one is the all the homeomorphisms up to homotopy, which fix this point x, and the left hand side is the fundamental group. So one has to be a little bit careful here, because this fundamental group is basically the loops, and the mapping class group is the surface homeomorphism. But yeah, this can be taken care using this. This is sometimes called the push map, and this is the forget map, because you are forgetting the point x, because this is the marking in the surface, and you are forgetting. So you'll get a natural surjection and this. So once says that, so we got the first theorem that if you have infinite type surface, already for finite type surface, we know that it satisfies the R infinity property. So now suppose the surface is infinite type and genus is 0. So we have seen some example, genus 0, genus finite, genus infinite. So I'll state the result for genus 0, and for infinite genus and finite genus, there are other techniques to go about this R infinity. And also I'll prove this result using some kind of induction. So the number of punctures on the surface, I'm assuming countable. So then this group has the R infinity property. So what is the idea? Proof idea is, in general, again, this has been used in the proof of the finite type setup. So suppose you have a short exact sequence of groups, where the left hand side, the normal subgroup is characteristic, and the quotient group has the R infinity property, then the middle one has the R infinity property. So we'll use this technique because that's what this BIRMAN exact sequence says, that you have a short exact sequence. You have a surface with a puncture x, and then you forget. So this is the mapping class group, and then you have this sequence. So in order to prove that the mapping class group of the middle one has the R infinity property, you have to prove that this group, the right one, has the R infinity property, provided the fundamental group is characteristic. Already we know that automorphisms are inner, or there is one outer. For inner, this is fine. For outer, you have to check. So this is the lemma we check, that this is in fact characteristic subgroup, and then you prove that this right side group has the R infinity property. So then the middle one has the R infinity property. Okay, so actually this proof gives almost nothing. This is like a general technique. So let me give a concrete example how it goes. So you look at this surface, R2 minus Cantor's. This is one of
Sushil,
yes.
but 3 minutes remaining now.
Oh, okay. Yeah, I am almost, like, I think I'll be done. Okay, thank you
Sure.
very much. Yeah. So, okay. So let me just give this example in 2 minutes. And so you take the surface R2 minus Cantor set. So you remove the Cantor set from R2. This is same as you look at the sphere minus the north pole, and you remove the Cantor set. These two are like homeomorphic. So their mapping class groups are same. So this north pole n, this is like, will work as x, which is the puncture. This is like, here the puncture is just 1. This is like the base step. So now look at this sequence. So R2 minus C is like the sphere minus a Cantor set with this marking the north pole, and you have a sort of exact sequence. And then if we can prove that the mapping class group of sphere minus a Cantor set has the R infinity property, then the mapping class group of R2 minus Cantor set has the R infinity property. But how to prove that the mapping class group of sphere minus a Cantor set has the R infinity property, which is this. So there is another short exact sequence which I haven't defined this group left hand side. Forget about this group. So there is a sequence. So this is the homeomorphism of the Cantor set, and there is a old result that proves that all the automorphism of this homeomorphism of the Cantor sets are inner. Therefore, it has R infinity property provided there are infinitely many conjugacy classes. In fact, by Anderson, they proved that there are infinitely many. So it says that the mapping class group has the R infinity property. So this is the concrete example to prove that the mapping class group of sphere R2 minus characteristics are infinity property. So yeah, so this is the result. So there are other results I won't say. Most of the infinite type surface has the infinity property. So for example, genus 0, I gave a proof. What is the idea using BIRMAN exact sequence? For genus 0, positive and finite always has the infinity property using some other technique of geometric group theory. For example, in the example I have seen the tripod surface. This is like infinite types of surface, and this has the infinity property. In fact, if it has at least 3 ends, then it has the infinity property. So okay, I think I am done. Thank you very much.
Let's thank the speaker. Are there any questions?
Can I ask?
Yes, please.
You mentioned that automorphisms of MCG plus is isomorphic to MCG, right?
Yes, yes, yes.
So is the center of MCG trivial?
Yes, yes, yes. So I haven't said that mapping class group center is trivial. Yes.
Okay. Another quick question is there a smooth version of mapping class group in the
So for a surface, homeomorphism modulo homotopy is same as diffeomorphism up to isotopy. So this is the result.
Is the result known there or?
Yes, yes. The result is old result due to Epstein. I think around 80s or even before that. That the diffeomorphism group is smaller than homeo, but up to isotopy they are same. Like the homotopy and isotopy, these class are same in the two-dimensional situation.
So the result is what is the result then?
So then result is, if you look at a surface, like the smooth surface, you put some smooth structure, and let's also assume orientable. And then you look at the diffeomorphism of that surface and go modulo isotopy.
Yeah.
This is same as you look at the homeomorphism of the surface, forget about the smooth.
No, I understood that. I'm asking about the R infinity property. It's the same. It is R.
Yeah, because the groups are isomorphic. Yes.
Okay.
Yes.
Okay.
Yes. Yes. Yes.
Thanks.
Oh, okay. Yeah. Yeah. But that is only for two-dimensional situation.
Right.
Yeah.
Okay. Thank you.
Okay. Thank you. Nice question, actually.
Are there any other questions? If not, then I have a general question actually. Sushil, you have done work on twisted conjugacy in Chevalier groups, in algebraic groups.
Yes.
And one paper of Shankaran makes a comment that this question of twisted conjugacy seen for different groups uses different techniques.
Yes.
So do you think this is true? Meaning you have worked with two different types of groups. Are there different techniques completely that are used?
Completely. For this group, this is not linear. Like it's
Yes.
completely non-linear group. So we use no linear technique actually. So we use that. So the proof I presented, this is the easiest one. Like algebraically one can think. The other technique that for suppose you have a G-genus surface and you remove a Cantor set. So therefore it's infinite type. So zero genus but finite. Also genus is finite. Not zero but finite. So for this technique mostly will not work. So for that, we find out some Gromov hyperbolic delta hyperbolic space, like negatively kind of space, manifold. And then we, not manifold, like the metric space, which is negatively curved. And then the group acts some non-elementary way. And then using some geometric result, we prove that this kind of surface also has the R-infinity property, like the mapping class group, for example. So for example, this tripod surface, again, so in the BIRMAN exact sequence, this has no isolated puncture. So that is like no use of this BIRMAN exact. So they are also use the same technique, but yeah. So like Gromov hyperbolic space on which the space act, and then some technique of geometric group theory we used. So again, yeah, the number of conjugacy classes also was not clear to me, like how to prove.
Correct, yeah.
So that's we use the translation. Yeah.
Okay, are there any other questions? If not, then let's thank the speaker again for a nice talk.
Thank you for listening. Okay, so
Radhika, are you there?
Yes, I'm here. Am I audible?
Yes, we can hear you.
Shall I share?
Yes, please share your slides. Are you ready?
Yes.
Okay. So our next speaker today is Dr. Radhika. She was a student here at IIT Bombay, and now she is a postdoc at TIFR, the Tata Institute of Fundamental Research. And she will be talking about congruent subgroup problem. Over to you, Radhika.
Yeah, thank you, Shipar. And I thank the organizers for giving me this chance to talk. Okay, so as the title states, it is the congruent subgroup problem. It is one of my, this is my thesis problem. And let's begin with some notations, standard number theoretic notations. So K will denote the algebraic number field, which is contained in the complex numbers. V will denote the inequivalent valuations of K. Infinity will denote the Archimedean places, and VF will be the non-Archimedean places. And for any V, you have KV will denote the completion, and in the non-Archimedean places, OKV will denote the ring of integers. S will always stand for a subset of V, which contains the Archimedean place. And you define the ring of S integers as all points in K, which are integral outside S. So these are the standard number theoretic notations. Now G will stand for a general linear algebraic group over K, and we'll fix an embedding of G in GLNC. So once the embedding is fixed, one has that GK is G intersection GL and K, and we'll define gamma to be the S integral points, which is given as GK intersection GL and OS. Now for any non-zero ideal A in OS, one can consider the homomorphism of GL and OS to GL and OS mod A. This is the reduction modulo A, and what is written down here is precisely the kernel of the homomorphism. And this kernel intersected with gamma is what we call as the principal congruence subgroup of level A. Now, a subgroup gamma prime of gamma will be called an S-congruent subgroup if it contains gamma A for some non-zero ideal A. And what is immediate here is that gamma prime is a subgroup of finite index in gamma. And gamma prime will be called an S-arithmetic subgroup if it is commensurable with gamma A for some non-zero ideal A. So by commensurability, one implies that gamma intersection gamma prime intersection gamma A has finite index in gamma prime and gamma A. So given that S-congruent subgroups have finite index, one has that all S-congruent subgroups are S-arithmetic subgroups. We'll formulate what the congruent subgroup problem is. So in the classical form, the congruent subgroup problem asks whether every S-congruent subgroup, whether S-congruent subgroups exhaust the S-arithmetic subgroup. So in this classical form, it was investigated in 1887 by Frick and Klein for the group SL2, and they considered S infinity, and their results they're negative. So for SL2Z, it turns out that there are a lot many homomorphisms to the alternating group, which have finite kernels, and these kernels are not S-congruent subgroup. So a reference to this will be Keith Conrad blog. So he has notes for SL2Z where he describes all these homomorphisms. Now, so much of these techniques which were used to prove the congruent subgroup problem in negation for SL2Z could not be carried forward for SLN in general. So this problem was sort of stagnant until 1960, when Bas-Lassalle and independently Menique, they proved that for gamma SLNZ, n greater than equal to 3, the congruent subgroup property holds. The first generalization of congruent subgroup property to this problem to number fields or in fact, to any general algebraic groups, came with the paper of Pascal Nassé. They investigated gamma for the groups gamma equals SLN OK and SP2N OK. We'll shortly see the results of this investigation. A little later, in 1970, Sayre studied the group gamma equals SL2 OK. So in this paper, he devised a method to measure the deviation from the congruence subgroup property. So an algebraic group which satisfies the congruence subgroup problem is said to have the congruence subgroup property. So here CSP will, I will occasionally use this acronym to refer to congruence subgroup problem and sometimes to congruence subgroup property. So how to measure this deviation from the congruence subgroup property? So for that, we endo GK with two topologies. So one is the S-congruence topology, where the fundamental system of neighborhood is of identity will be given by the S-congruent subgroups. And the other is the S-arithmetic topology, where the fundamental system of neighborhoods of identity will be given by the S-arithmetic subgroups. Now one can consider the completion of GK with respect to these topologies. So if G hat denotes the S arithmetic completion and G bar denotes the S congruence completion, one has that the identity map so the identity map from GK with the S arithmetic topology to GK with the S congruence topology extends to a unique to a continuous homomorphism from the completion, arithmetic completion to the congruence completion. So it turns out that this map, which I refer to as epsilon, is surjective, and this extension is because we have seen that every S congruence subgroup is S arithmetic subgroup. So because this map is surjective, one has the short exact sequence with a kernel, which we call as the S congruence kernel. Now it can be shown that the S congruence kernel is trivial if and only if the two topologies coincide. So according to Sayre, the congruence subgroup problem is defined, can be reformulated as to determine the kernel for a given G and S. So henceforth, we'll be talking about what this kernel is. And there are certain properties of this kernel which will help us reduce the problem of this, the congruence subgroup problem for general algebraic groups. So first and foremost, we will see that the topologies that we defined, the tau A and tau C, the arithmetic and congruence topology, this can be, this is in fact defined on GOS, as we have defined as congruence and as arithmetic subgroups inside GOS. And we can also consider the arithmetic completion and the congruence completion of GOS with respect to these topologies. And this will give a similar exact sequence with a kernel. And it turns out that this kernel, the kernel that we determined with considering GK, coincides with this kernel. So now this is a profinite group. So this is the inverse limit of GOS with respect to normal subgroups, and this is the profinite limit with respect to the congruent subgroups. So this helps us conclude that the kernel is actually a profinite group. Now, now the next property is that one can see that by definition, GK embeds in the congruence completion and in the arithmetic completion. So this gives a splitting of this exact sequence over GK. So sequence 1 splits over GK, and one has the action of GK on the congruence kernel. It turns out that in many of the cases, this action is trivial. So that helps to conclude that the extension CSG is central in G hat. And the next thing to observe is that the kernel is independent of the choice of embedding G in GLNC. In fact, one has that this map G to G SG is functorial in the sense like if you have a K, isomorphism of K groups, one can get an isomorphism of the kernel of the congruence kernel. So this helps in reducing the general case of algebraic group to the absolutely almost simple simply connected group. So what happens is one knows that the congruence subgroup property holds for the additive group GA. And with that, you can conclude that for unipotent group, it is the congruence subgroup property holds. So we have CSG is trivial when G is unipotent. And then one uses the Levy decomposition to reduce it to semi-simple group. And from the semi-simple group, you can show that okay, you can read of the congruence subgroup property, the congruence kernel from its simply connected cover. So that is how you reduce it to the absolutely almost simple and simply connected case. So from now onwards, we assume that G is almost absolutely simple, simply connected. Now, what does this congruence kernel look like? So in the case of SL2Z, we have seen that the congruence subgroup property fails, as was the work of Frick and Klein. And in this case, the congruence kernel is a profinite group, free profinite group of countable rank. This is a work by Menike. And in the case where the congruence subgroup property holds, the kernel is trivial. Now, in general, one has this result that if G is K isotropic with S rank G greater than or equal to 2, then the congruence kernel is trivial when S contains a non-complex place and is the cyclic group of roots of unity in K otherwise. So by S rank G greater than 2, this is defined as the K, summation of the KV rank for V in S. So this theorem is due to many people. So for example, in the case of SLNC, this was due to Bas Milner said. For SL2, okay, it was due to said result, and then Matsumoto did it for K-split groups, and Rasmussen did it for non-split groups, and Prasad and Raghunathan together they did it for they determined the CSG is identity NUK for a general K isotopic groups. Now a similar so here for a K isotopic group, one has a nice description, but a uniform description. But for K anisotropic groups, such a uniform description does not exist. So I will not be stating what the kernel looks like, but one knows that whenever the kernel is finite, it is either identity or it is roots of unity. But such a description might not. There's no uniform description with that. Now in the anisotropic group, okay. So the first result came by Messer, and he did it for G, which is G when G is a spin group of the quadratic form with more than 5 variables, and F is such that F is isotropic at all places, all non-Archimedean places in S, and S rank G is greater than or equal to 2, then the congruence subgroup property does not hold. And this method was also used by Rapinchuk and Tomino to deal with the cases of DN, CM, and DM, and also for special unitary groups of Hermitian forms over quadratic extension of K. And later on, was not the same method, but the exceptional groups were dealt by Chermazov, Rapinchuk, and Platonov. So in all these cases, S is V minus S naught, where S naught is the place where GKV is compact. That is all places where it is anisotropic. G is KV anisotropic. So now, based on Nesser's work and a few earlier results, Sayre postulated a conjecture. So for G anisotropic, G absolutely almost simple, simply connected, and isotropic at all non-Archimedean places, one has CSG is finite if S rank is greater than equal to 2 and is infinite if S rank is equal to 1. Now we'll see what is the progress in Sayre's conjecture. As we have seen already for anisotropic cases, yeah, it is done here for Bn, Cn, Dn, and it is also dealt with for exceptional groups. And now what is left is, it is not dealt completely for groups of type An and for triality groups T4 and exceptional group E6. However, some progress has been made in type An. So we let S not be the places where, as I mentioned earlier, where G is KV and isotropic, and it is seen that CSG will be trivial in those cases when G is of type An, inner type An. So this is a result by Platner, Rapinchuk, Raghunathan, Sagate and Seeds for general An, and Margulis dealt it for A1. And Prasad and Rapinchuk in a recent work showed that CSG is trivial when S is a set of valuations in arithmetic progression. What I mean by valuation in arithmetic progression is if L is a Galois extension of K and sigma is an element in the Galois group. So, so all those places where the Frobenius element falls in the conjugacy class of sigma. So this is a particular case of this. So such a set will be called a set of valuations in arithmetic progression. And Prasad and Rapinchuk showed that if S is set of is such a set, then the congruence kernel is trivial for G in the type An. And my work with Raghunathan showed that when S is D-amenable, then the CSG is trivial for inner type An. So by D-amenability, what I mean is that for every extension of degree D, one should have that if W is the complement of S, one should have that this quotient has a exponent which divides a particular number. So this might look like a strange condition, but the fact that we use some kind of an approximation result of K star to prove the centrality of the congruence kernel, it is necessary that one be able to approximate the elements of KW plus by K bar star. But what happens is when S is finite, the strong approximation property does not hold for K star. So we have this exponent term coming in, and as a corollary, we have that if complement of S is a finite set which contains S naught, then the congruence of group kernel is trivial. And the triviality of the congruence kernel was proved for anisotropic type Bn, Cn, and Dn, as here for V minus S finite by Surin. Now we'll see what goes into the proof of the congruence subgroup problem. So the thing is like we will first identify what the congruence completion looks like. So if AS denotes the ring of S adales in KV, so we will basically set up all XV in product KV. XV belongs to OKV for almost So this can be called, this is referred to as a restricted product of KV with respect to the ring of integers OV. So one can similarly define the ideal points of GAS. This will be the restricted product of GKV with respect to the integral points. Okay, and it turns out that it turns out that the S congruence topology on G is same as the on GK is same as the topology that GK inherits as sitting inside. So GK embeds diagonally into GAS. And the S congruence topology is same as the induced topology, which we call as the S-adic topology. Now, because we are looking, we have the condition that G is KV isotropic for all V in S. We have a strong approximation. The GAS, strong approximation holds for GK, and which basically says that GK is dense in the ideal points. So one has that the closure of GK in the static closure of GK is GAS, and which is the same as the S congruence closure. So plugging in GAS in place of S congruence closure, one gets the following exact sequence. So this is basically a topological extension of a ideal group with a profinite group.
Radhika, you have 3 minutes now.
Yes, thank you. So I'll just tell what, in another 2 minutes, I'll just say what is that group. So there's no uniform way of proving the centrality of the congruence kernel. But once you prove the centrality of the congruence kernel, that is one has to show that this congruence kernel is central in G hat. Once you prove that, then it turns out that it is the contragent dual of the congruence kernel is isomorphic to this kernel of the second cohomology group. It is a continuous cohomology of GAS with points in Q mod C to continuous cohomology of GK with points in Q mod C. So this kernel is completely determined by Prasad Raghunathan and Prasad Rapinchuk. So Prasad Raghunathan determined it for the K isotropic case, and Prasad Rapinchuk determined it for the remaining cases. Now, one of the main ingredients which goes into proving the centrality of CSG is the normal subgroup structure of GK. Now, the normal subgroup structure of GK is determined by the Margulis-Platonov conjecture. So basically, when G is K anisotropic, one has that any non-central normal subgroup of GK is can be realized as pullback of an open normal subgroup in GS0. So here delta will be the diagonal embedding of GK in GS0, and when G is K isotropic, it is G has no non-central. No non-central normal subgroups. So one has a GK is simple modulo its finite center. And as one can see that when S is the complement of the anisotropic places, then the congruence of the problem coincides with the Margulis-Platonov conjecture. So how this is relevant is that once you have the MP conjecture, and once you know that the congruence kernel is central, then you can show that it is finite. And once it is finite, it is either identity or it is the roots of unity, the cyclic group. And the other way around is once you have the NP conjecture and once you know that it is finite, then the congruence kernel is central. So the centrality is equivalent to proving that it is finite. And once finite, it is completely determined what it is. So I think I will stop here. Yeah. Thank you for listening.
Let's thank Radhika for a nice talk. Are there any questions?
I just wanted a clarification on the Sayre's conjecture you mentioned. So you said it's open. So is it open for all TITS indices, or some indices the answer is known?
It is known completely for the rank 1 case is completely dealt with. And in the higher rank case, it is the outer forms of AN is open.
What I
For
mean
inner,
is E6
yeah.
and 36D4 AN, these three groups
Yeah.
you mentioned. So
Yeah, these
in some cases it is known, is it?
364.
Yeah. Or E6.
I'm not sure because I haven't come across.
Okay.
Yeah, I mean for these both I haven't come across any cases where it is.
Okay, thank you.
Any other question or comment? Okay, let's thank Radhika once again.
Thank you.
Arunava, are you there? Yeah.
Yeah.
Do you want to just share your slides? There is still some time, 1 or 2 minutes, so we will wait, but you may share the slides.
Okay. Let me put on the light. Is it okay? Fine.
Yes, we can see it. You need to go to the first page. We will wait for a minute,
Yeah.
and then I will introduce you. Yeah. Okay, maybe it is time. So our next speaker today is Dr. Arunava Mandal. He was also a student here at IIT Bombay, and after completing his PhD, he was at ISI Delhi and ISI Bengaluru for some time. Now he is at ISER Mohali. He will speak on the structure of Kartan subgroups in Lie groups. Over to you, Arunava.
Yeah, thank you, Srivard. And thanks to the organizers for giving me this opportunity. Okay, let me start. The title of my talk is The Structure of Kartan Subgroups in Lie groups. Kartan subgroups is a classical object in Lie theory, and it captures crucial properties in Lie groups. Now, I will mainly present our recent work with Riddhi Shah about the structure of Cartman subgroup. Here are the objectives. First, I will give a brief introduction of Cartman subgroups in Lie groups, mainly definition, some examples, and few facts. Next, I will concentrate only concentrate on our work. One of the main motivation of our work is coming from Ushner decomposition theorem on Cartman subgroups, and we will provide some characterization on Cartman subgroups which generalizes that Ushner structure theorem. Moreover, we will describe a recipe for constructing Cartman subgroups in solvable Lie groups. And that will be the main tool, main technique to get some more decomposition results on Cartman subgroup. Next, we will talk about the Cartman subgroup in quotient group. Finally, I will discuss an application in the density of the images of the power map. Let me begin with the definition of Cartman subgroup. Yeah. A subgroup C of a Lie group G is said to be a Cartman subgroup if it satisfies following two conditions. First, C is a maximal nilpotent subgroup of G, and second, if L is a normal subgroup of finite index in C, then it is finite index with its own normalizer. The point here is to note that L is a normal subgroup in C. It is not a normal subgroup in the whole group. This definition is due to Chevalier in 1955. Now I will give some examples. Suppose our group is compact and connected, then the maximal tori are the Cartman subgroups. For SL2R, we can see that there are two types of Cartman subgroups, namely SO2R and the diagonal, that AA inverse. But if we take our group to be a connected nilpotent group, then Cartman subgroup is itself. Now we can discuss a little more complicated example. Suppose G equal to a one parameter subgroup, G is equal to semi-direct product of a one parameter subgroup P and a vector group. Vector group means it has a group structure and vector space structure as well. Suppose the P action on P is irreducible and non-trivial, then one can see that all Cartman subgroups are of the form WPW inverse, where P is WPW inverse. Basically, this is P or its conjugate. So one can probably understand that there is a deep connection between Cartman subgroup and Cartman subalgebra. Probably guess that. So let me define what is Cartman subalgebra. A Cartman subalgebra in a Lie algebra is a maximal nilpotent subalgebra which is its own normalizer. It is clear from the definition of Cartman subgroup that its Lie algebra is a Cartman subalgebra. We know that given a Lie group G, there always exists a Lie algebra, and there is a natural exponential map from Lie algebra to a Lie group. Now, if we take a Cartman subalgebra and take its image under the exponential map, then it is equal to the connected component of Cartman subgroup. Because exponential map is continuous and Cartman subalgebra is connected, so it can reach up to the connected component, but it will not cover the whole Cartman subgroup. But there is a 1-1 correspondence between a Cartman subalgebra in a Lie algebra and a Cartman subgroup in a Lie group. That was proved by Chevalier in 1955. Okay. Though in this talk I will mainly use the definition due to Chevalier, but in literature there are other definitions of Cartman subgroup. I want to say few words about this. This is another definition of Cartman subgroup. Suppose G is a Lie algebra and that script C is a Cartman subalgebra of script G. Now, if we take the if we complexify that C and we can get root space decomposition, then we can get a root space decomposition, and delta is the set of all roots. Now, the notation C of the script C is equal to all those G in normalizer such that it commutes, at G commutes with its roots. A closed subgroup C of a Lie group G is called a Cartan subgroup if its Lie algebra is a Cartan subalgebra of G and CC equal to C. That the notation CC defined above is equal to C. It is important to note here that these two definitions are not equivalent for disconnected groups in general. Because you can take a discrete group, as long as it is not nilpotent, it is not going to be a Cartan subgroup according to Chevallier's definition. Whereas if we use this definition, the discrete group is always a Cartan subgroup. So therefore, these two definitions are not equivalent in general. However, Neve proved in 1996 that these two definitions are actually equivalent for any connected Lie group. As I said earlier, that Cartan subgroup is a classical object. It was studied by many peoples. Bodel, Togo, Goto, Neve, Rinkelmann, Ushnar, and in different contexts they are studied by Prasad, Raghunathan, Hoffman, Mukherjee, Pralay Chatterjee, Dani, Bhomik, and by many others. Bodel has done an extensive study of Cartan subgroup in the context of algebraic groups. And in the context of algebraic groups, Cartan subgroup is the centralizer of a maximal torus. But if we restrict our group to be a semi-simple group, then centralizer of maximal torus is equal to the torus, and hence torus is the only Cartan subgroup for semi-simple group. Now I want to give here some few more basic facts. Cartan subgroup for a connected Lie group, Cartan subgroup always exists. Recall that Cartan subgroups by definition it is a nilpotent group, but if our group is a semi-simple and its center is trivial, then Cartan subgroups are always abelian. However, there are examples, there are semi-simple groups whose Cartan subgroups are not necessarily abelian. Of course, any conjugate of a Cartan subgroup is always a Cartan subgroup, follows from definition. The center of a group is always contained in every Cartan subgroup, because if not, then you can multiply the center, because it is abelian, you can get nilpotent. So center is contained in every Cartan subgroup. The union of all Cartan subgroups is dense in G. Of course, this is not a group, this is a dense set in G. Okay. If we take G to be a compact, solvable, or complex connected Lie group, then Cartan subgroups are always connected. However, this is not true in general, meaning Cartan subgroup need not be connected in general. As we saw before that for SL2R, there is a Cartan subgroup, the diagonal matrices, then it has clearly two components. So, given a Lie group G, Cartan subgroups need not be connected. It has finitely many connected components, and it has also infinitely many connected components. For example, if we take that universal cover of SL2R tilde, then universal cover of SL2R, then the extension or lift of some Cartan subgroup has infinitely many connected components. But Cartan subgroups are always connected if and only if G is weakly exponential. What is weakly exponential? If the image of the exponential map is dense in G. Bodel proved this fact for semi-simple group, and then later Neve and Hoffman extended to any general Lie group, connected Lie group. Now I will state Ushna decomposition theorem on Cartan subgroup, and I should say this is the main base point of our study. To state this theorem, I want to define some terminology. What is Levy subgroup, what is radical, and what is Levy decomposition. So let me define what is radical. Given a Lie group G, there is a maximal connected solvable normal subgroup of G, and then it is called radical, and it is unique, and it is always exist. So given a group G, radical always exist, and if radical of a group is trivial, then we can say that group is semi-simple. A Levy subgroup S of a connected Lie group G is a maximal connected semi-simple group of G. And for consistency, we should include that it is trivial if G is solvable. Now, what is Levy decomposition? Levy decomposition says that for a connected Lie group G, G can always be written as SR, where S is a Levy subgroup and R is the radical, and their intersection is discrete. Now, we can state the Ushna theorem. So, G be a connected Lie group, R be the radical of G. If C is a Cartan subgroup, then we can get the following. There is a Levy subgroup S in G such that C can be decomposed as C intersection S times C intersection R. So our starting point here is a Cartan subgroup C in G, and Ushner says that there is a Levy subgroup S in G such that C can be write in this way. Moreover, C intersection S is not any group, it is a Cartan subgroup of S. And that C intersection S commutes with the elements of C intersection R. And C intersection R is connected. Note that Ushner theorem does not tell anything about C intersection R except it is connected. So we can ask the following question, whether that C intersection R is a Cartan subgroup of R. So one can ask this question in general point of view also. Given a G and a radical R, this is sort of an invariant question. Given a group G and C and R is the radical, suppose C is a Cartan subgroup of G, whether C intersection R is a Cartan subgroup of R. The answer is no in general. We can show by an example. So let G equal to SL2R, semi-direct product with a Heisenberg group, three-dimensional Heisenberg group. This is a 3x3 upper triangular matrices with 1 on the diagonal. I am not written here the action, but the action is the SL2R action on the center of H is trivial. So it will be a normal subgroup in G. So SL2R acts on H mod the center, and H mod center is isomorphic to R2, and their multiplication is usual matrix multiplication. With this action, Cartan subgroups of G turns out to be that C equal to CS times direct product with the center, where CS is any Cartan subgroup of SL2R. So it is clear that for this group G, the radical is H, and it is nilpotent, and hence Cartan subgroup is itself. On the other hand, the Cartan subgroup of G is CS times Z, so C intersection R is only that Z. Therefore, it is a proper. It is not a Cartan subgroup of R. But we can observe for this particular example that it might happen that C intersection R is not a Cartan subgroup of R, but it is contained in a Cartan subgroup of R. So that will be our next question. C be a Cartan subgroup of G and let R be the radical. is C intersection R is contained in a Cartan subgroup CR of R. We can ask more general question. We can replace that radical by any closed connected normal subgroup. If H is any closed connected normal subgroup of G, then is C intersection H contained in a Cartan subgroup of H? We can ask another question that is sort of a converse of Ushner result. What Ushner result? You recall that Ushner gives a decomposition of a Cartan subgroup C in G. If you start with a Cartan subgroup C, then C can be decomposed as C intersection S times C intersection R, where CS is a Cartan subgroup in S. But now we can ask the sort of converse question, and that is, given any Levi subgroup S of G and a Cartan subgroup CS in S, can we extend it to a Cartan subgroup of G? Now we will answer the above questions, and I should mention that this is a joint work with Ritisha. So probably one can observe that to answer all of these questions, one need to study C intersection R more carefully. What sort of object this is? We need to understand that. So for that, we first concentrate. We are not considering first a general Lie group. We concentrate first for solvable groups. And we, And I should say that this proposition is one of the main tool to get our further characterization on Cartan subgroup. So I should spend a few more minutes on this proposition. So suppose G is a connected solvable Lie group, then there always exists a maximal nilpotent connected normal subgroup of G, and it is unique and it is called nilletical. So given a G, we can get a nilletical N. Suppose T is a largest compact connected central subgroup of G. And we are taking that G is equal to Ln, where L is a nilpotent subgroup complement to the nilletical. Then we can get the following. The normalizer Nn of L0 T is connected, and normalizer of L0 T in G is also connected and nilpotent. Moreover, L is contained in a Cartan subgroup of G. This is the first part of this proposition, and second part says, suppose G equal to Mn, but I am not assuming M here is nilpotent. Then any Cartan subgroup Cm of M is contained in a Cartan subgroup C of G. Moreover, Cm is equal to C intersection M. So let me give a brief idea of the proof. To prove 1 and 2, we may assume that N is simply connected. That we can do always. And to say that this group is nilpotent, it is enough to prove that Ng of L0 is nilpotent, but Ng L0 can be written as L0 times Nn L0, and since they are normalized each other, so it is nilpotent. And for connectedness, we need some more works. I will not go into that. But the main crucial part of this proposition is the second, that given a L, how one can get a Cartan subgroup containing that. So we are starting from L, then we are taking a normalizer. We know by 1 that it is connected. Then again we can take a normalizer. Thus, we can get a tower of normalizer. Since dimension is increased because of this dimension, it should stop somewhere. and the final product we claim that will be the Cartan subgroup. That is the main idea. So the tower should stop somewhere, that is Ln, and note that Ln is equal to here normalizer. So for a solvable group, Cartan subgroup is actually equal to its normalizer. So our claim is that Ln is a Cartan subgroup. So how one can show that? Well, we can use Severus definition. That means we should show that this is a maximal nilpotent group, and we will use for that if Q is a proper subgroup of a nilpotent group M, then Q is a proper subgroup of its normalizer. By using because if Ln is not maximal, then it is contained in some maximal, and then taking normalizer on that and use this fact, we can get that Ln is a Cartan subgroup. Yeah, once we get that L is contained in a Cartan subgroup, 3 will follow, because G, here G equal to Mn, and G can be further written as Cartan subgroup of M times N, and that Cm by 2, it is contained in some Cartan subgroup C, and it will follow that Cm is actually equal to C intersection M. Okay. So as a corollary for a solvable group, we can say that C is a Cartan subgroup of G if and only if C is connected, nilpotent, and normalizer equal to C. We can get some results, topological properties of that. The notations are as above. G is any group, S is Levy subgroup, R is radical, and CS is a Cartan subgroup of S. Then centralizer of CS in N and centralizer of connected component of centralizer in N are connected. ZRCS, that centralizer of CS in R, is also connected. Moreover, R can be written as centralizers times N. Yeah. Now we will give the characterization result. Sort of, we mainly focus the converse part of the Ushner result. What it says.
So 3 more minutes remaining, Arunava.
What?
3 more minutes.
Okay.
Yeah.
Suppose G equal to SR, this is a Levy decomposition, and CS, we are starting with a Cartan subgroup of CS in S. Then can we extend it to a Cartan subgroup of the whole group? That is our main question. Now we said that it says that ZRCS is connected, and if we start with a CS and then we multiply with a Cartan subgroup of ZRCS, then the whole product is a Cartan subgroup of G. Moreover, any Cartan subgroup of C is arises in the above form. So one can guess that one can recall the Ushner decomposition theorem. C can be written as CS times C intersection R, and here the main work, we relate C intersection R with the Cartan subgroup of ZRCS. Now we can get one more characterization. Suppose G is a Lie group and R is the radical, and suppose TR is a maximal compact subgroup, then by Goto it is contained in a Cartan subgroup, and by Ushner we can see that this is a central in C. But in this we can say more that that centralizer of TR in G is connected. Moreover, we show that there is a one correspondence between the Cartan subgroups of G and Cartan subgroups of centralizer of TR in G. So it says that every Cartan subgroup of ZGTR is a Cartan subgroup of G. Conversely, every Cartan subgroup C of G is a Cartan subgroup of centralizer of some maximal compact subgroup. Okay. So using that and using the above characterization, we can refine our statement further, that we can relate that C of ZRCS is, we can see that a Cartan subgroup of ZRCS is actually Cartan subgroup of ZRCS times TR. So we can refine that statement, same statement, in this way. as we asked above before, that as we saw before, that given a Cartan subgroup C and a radical C intersection R need not be a Cartan subgroup, but whether this is contained in a Cartan subgroup of R or not, the answer is yes, and we can prove more general result that if we take H to be any closed connected normal subgroup of G, then C intersection H is contained in a Cartan subgroup of H. And if H is solvable, then C intersection H is connected, moreover H can be written as C intersection H times its nil radical. Using this proposition, we can further decompose our Cartan subgroups, and that Cartan subgroup C can be written in this following form. So it says that there exists a Cartan subgroup CR of the radical R such that C can be written as CS times ZR CX intersection CR, because that R can be written as ZR CS times M. On the other way, given any Cartan subgroup C, there exists a Cartan subgroup CR such that C intersection R is equal to C intersection CR. The converse part also true, meaning if we start with the Cartan subgroup CR in R, we can find a Cartan subgroup C such that this equality will hold. In the quotient proof, we can get that suppose C is a Cartan subgroup of G, then the quotient CH mod H is a Cartan subgroup of G mod H. Conversely, if Q is a Cartan subgroup of G mod H, then there exists a Cartan subgroup C such that CH mod H is actually equal to Q. Now I will give an application, the application on density of the power map. So what is the power map? That power map Pk from G to G is defined by x goes to x power k, and our theorem says that for a Lie group G and H is a closed normal subgroup, if PKH is dense in H and PKG mod H is dense in G mod H, then PKG is dense in G. And we can reprove Hoffman-Mukherjee's result about weak exponentiality from it. So it says that G is a connected Lie group and H is a closed normal subgroup. If H and G mod H are weakly exponential, then G is weakly exponential. Of course, the converse of this theorem is not true. Yeah. Now I should stop here. This is the main reference of this talk. And yeah, thank you. Thank you for your attention. And yeah.
Let's thank Arunava. Thank you, Arunava. Are there any questions or comments?
Yeah, I am learning this subject, so I want your advice, comments, remarks, etc. So,
I have a general question. So, are the similar results true for Lie algebras also?
Yes. No. Maybe more precise you can ask. Then.
No, yeah, anything that you know.
Actually, no. There are so many results, and one can in Lie in the context of Lie algebra, but not this particular one.
If you take a Lie algebra and you take a Carta subalgebra in it and take the Levy decomposition of the Lie algebra, do the intersections always form Carta subalgebras?
Which one? That no.
Not always.
No.
But can we say something more? Because the radical can be nilpotent, and so of course one can understand that the intersection will not be Carta in the radical.
Yeah, actually that will follow from our work also. Meaning we can prove that group level and come back to the Cartan subalgebra level.
Okay.
But the other way around, little bit difficult because of Cartan subgroup is not exponential. Suppose you get once when we start this problem, one should think about the Cartan subalgebra level, the same problem, and then try to use the exponential map. But under exponential map, we can reach up to the connected component, not in the whole group. So that's why we did it for group level using that Chevalier definition. And of course, if we get that group level things, then we can back in real algebra level easily. The same result will hold in real algebra level, in analogous result. Yeah.
Okay, good. Any other comment or question? All right, so let's thank Arunava once again for a nice talk. We will now have a coffee break for half an hour. We'll resume at 4 p.m.
Shipad, you're mute.
Thank you. So our fourth lecture today is given by Dr. Tushar Kanta Naik from ISER Mohali. Tushar did his PhD at HRI.
Shipad, you're mute.
Am I still mute?
No,
Thank you.
You are audible.
So our fourth lecture today is given by Dr. Tushar Kanta Naik from. Am I still mute? I think I could hear myself.
I can hear you.
Okay, great. So Tushar did his PhD at HRI, Prayagraj, and he is at ISER Mohali now. He will be speaking about automorphisms of odd Coxeter groups. Over to you, Tushar.
Thank you, Professor Garge. I also like to thank the organizers for this wonderful opportunity. As the title suggests, I will be speaking on the automorphisms of some odd Coxeter groups. This is joint work with my PDF mentor, Dr. Mahinder Singh. So this work was motivated by the famous Artin-Brad groups, twin groups, and their relation with the symmetric groups. So I am new to this theory of Coxeter groups, so I would love to receive comments from the experts. So my plan is to go through basic terminology related to a Coxeter group, associated graphs. Then I will state the isomorphism problems in Coxeter groups. Then I will connect the Artin-Brad groups and twin groups to odd Coxeter groups through the Coxeter presentation of symmetric groups. Finally, I will end the talk by describing the automorphism group of some odd Coxeter groups. So let's begin. Okay, so a group W is called a Coxeter group if it admits a distinguished generating set S for which the defining relations are only of the form SS prime to the power MSS prime equal to 1, where all MSS is equal to 1, and this actually makes the generated involutions of order 2. And the other condition is MSS prime equal to MS prime S, and they can be any finite integer greater than 1 or infinity. So we call the pair WS to be a Coxeter system, and the kernelity of the set S is called the rank of Coxeter system WS. So immediately we have a question that is a Coxeter system uniquely determined by the group W, Coxeter group W? Unfortunately, the answer is no. And here is an example that the Hadal group of order 4n, where n is greater or equal to 3 and an odd integer. So the first presentation is a standard presentation which we encounter mostly, but it can have the second presentation also. So next is exponent. We refer all the MSS prime with S not equal to S prime as the exponent of the Coxeter system WS. And this is not a universal terminology. Some people call them as bond also, but here we fix the terminology exponent. And we call the finite MSS prime as finite exponents. Next, for a subset T of S, the subgroup generated by T is called a standard parabolic subgroup of W, and any conjugate of a standard parabolic subgroup is called a parabolic subgroup of W. And it follows that a parabolic subgroup of a Coxeter group is itself a Coxeter group, which is not true for an arbitrary subgroup of W. So with this, we'll come to the first graph associated. So this gamma WS is an undirected labeled graph. And the vertex set is same as the genetic set S. And we put an edge between the vertices S and S prime if and only the corresponding MSS prime is not equal to 2. We can label all the edges and we just leave one edges where the MSS prime is not equal to 3. Where it is equal to 3, we leave this edge. We do not label the edge. It follows that if the graph gamma WS is disconnected, then the cluster group W becomes the direct product of its standard parabolic subgroups corresponding to each connected component of the graph. And if the graph is connected, we call W to be an irreducible cluster group. So with this, we are ready to state the isomorphism problem or rigidity problem. Actually, both are kind of similar, just reverse of one another. So we call a cluster group W to be rigid if for any two associated cluster system WS1 and WS2, the corresponding graphs gamma WS1 and gamma WS2 are isomorphic. So earlier we saw that the Hadal group of order 4n can have two distinct cluster systems and the graphs can be non-isomorphic. And rigidity problem is to decide whether a given cluster group W is rigid or not. And isomorphism problem is kind of a opposite one. So here we given two cluster groups, gamma W1S1 and gamma W2S2, we have to decide whether the cluster groups W1 and W2 are isomorphic or not. Okay, so there are some cases where the isomorphism problem has been solved. Okay. But to list them, I need to define a lot of other terminology, so I'll leave that. And I request the audience to see these two papers, one where Brady, Muller, Newman, McCommand, and the other is by Muller. So there are, in this paper, you find the recent objects on this isomorphism problem. And now we'll define another graph called VWS. So this is again an undirected level graph. And the vertex set is same as the generating set S. But here, there is an edge between the vertices S and S prime if and only the corresponding exponent MSS prime is finite. So here we label the edge between S and S prime by MSS prime if MSS prime is not 3. And in this case, if the graph is disconnected, then the cluster group W becomes the free product of its standard parabolic subgroups corresponding to each connected component of the graph VWS. So with this, okay. So let's see the status of isomorphism problem for odd cluster group. So let W1 S1 and W2 S2 be two odd cluster systems so that the corresponding graphs are trees. So the graph is tree means it is a connected graph without any loop. And in this case, W1 is isomorphic to W2 if and only they both have same rank and same multiset of finite exponents. Multiset means we count the multiplicity of the exponents. And this result follows by again the earlier paper, the Brady, McCowan, Muller, and Newman. So with this, we are ready to, okay, we see some application first. So these are the following three groups which are isomorphic. And it is not easy to decide from the looking into the presentation of these three groups. Well, in the first group, W, in all these relations, W1 is present. But in next to group T and S, this is not the case. So, but we can decide whether these are isomorphic or not by looking their graph V. So let's see the graph. So these are the three graphs. All these three graphs are trees. They are not isomorphic graphs, but due to the earlier result, the corresponding three groups are isomorphic. This actually makes the study of odd cluster groups a bit easier. But surprisingly, no attempts were made to study their automorphisms till now. And we now move to see the relation of twin group, dead group with this odd cluster group. So for that, let's look the Coxeter representation of SN. The symmetric group SN can be generated by the transpositions I plus 1, which we denote here by tau I, and it has following three kind of defining relations. The first one is involutions, all the generators are order 2. Second one is Baird relations, and third one is the far commutativity. That is tau I, tau j commutes, if and only if they are far apart. So with this presentation, we will now relate to Baird group and twin groups. So what is Baird group? So by omitting all relations of type 1, that is the condition that all the generators are involution, from the presentation of SN, we get the presentation of Baird group as follows. So this is a presentation of Baird group. So these Baird groups are well-studied objects and of much interest to knot theorists, topologists, as well as algebraists. Now we will move forward to the twin groups. So now if we omit the all relations of type 2, that is the Baird relations, from the representation of SN, we get the presentation of a group which is called twin group. So this is the presentation of twin group. These groups are also of interest to topologists, algebraists, and also physicists. Physicists call this group as trade groups. So now there is a natural question arises here, that what kind of a group do we get if we omit all relations of type 3, that is the far commutative relations, from the presentation of SN. And surprisingly, no one had attempted to study these groups. And here the answer is, if we remove all the relations of type 3, we will get this Coxeter group. And by looking at this presentation, we can conclude that this is an odd Coxeter group. All these exponents are 3. And its V graph is like this, the straight line. So with this group are of much interest to geometry also, but I will not go to that. Dr. Mahendra Singh has talked about that in his earlier talk in the groups Sangam series. So we come back to see the automorphism of this odd Coxeter group. So we consider this group W, where this is generated by n element and all generators are involutions, and this is the only kind of relation, that W1 and W2 is a product Ti. And this Ti can be, there can be repetition, so we set them like this: Ti equal to M1 for all I2 up to K1 2 to K1 plus 1, then M2 for K1 plus 2 to K1 plus K2 plus 1, and so on. So here all these Mi are all positive integers, and we consider n to be greater equal to 3, because for n equal to 2, this group W becomes a dihedral group, and its automorphism is well studied, so we leave that case. So we'll see why we choose this odd Coxeter group, because of this graph. So for this group W, if we consider the V graph, it becomes this graph, the star graph. So here this only W1 is occurring in the relation. So this, and we have labeled as with Ti, and we remove the Ti if the Ti is 3. So this is the graph V with respect to the group W we consider. Let's see its automorphism. So the inner automorphism group. So it follows from the Bourbaki books that the center of an infinite irreducible Coxeter group is trivial. And here is this W is an infinite irreducible Coxeter group, so its center is trivial, hence its inner automorphism group is isomorphic to itself. Now let's see a special automorphism group called as graph automorphism group. So an automorphism of the graph gamma WS extends uniquely to an automorphism of Coxeter group W, and such an automorphism we call a graph automorphism. And the set of all graph automorphism forms a subgroup denoted as aught gamma WS of the automorphism group of W. And by result of transcend, it follows that if W is an infinite Coxeter group, so that it does not have a finite parabolic subgroup as a direct factor, then this graph automorphism intersects trivially with the inner automorphism. So it means all the graph automorphism are outer automorphism. And in our case, note that we had considered a graph V graph, but here the graph automorphism are considered from the gamma graph. So, but we can see that the V graph of W is a subgraph of the graph gamma WS, which is a complete graph, because here there is no exponent is 2. So the graph gamma WS is a complete graph, and all the new edges which are not there in V are labeled as infinity. By a closer look, we can see that any automorphism of the graph V extends to an automorphism of graph gamma and vice versa. So this automorphism of graph gamma is isomorphic to automorphism of the graph V, and this can be seen from the graph that it is isomorphic to the direct product of symmetric group SK1, SK2, and SKL, where these Ki's are the multiplicity of the exponents. Basically, you can, if this T2 and T3 are same, then you can just permute this W2 and W3, these edges. So this is a graph automorphism of this group W. And as from this result, we can see that this graph automorphism lies outside the inner automorphism. Now we move forward to see the final, the remaining automorphism of W. So here we set Ci equal to, this is generated by this type of automorphism theta I k, where this k is relatively prime to Ti, and this is defined as this theta I k fixes all the generator Wj where j is not equal to I, but it takes the generator Wi to the element W1 times W1 Wi to the power k. Then we can see that this group Ci is isomorphic to the multiplicative group of integers modulo Ti and coprime to Ti. Then we take all such Ci and take their direct product, that is at C. So again, we can see that C is the direct product of these groups ZTi, and this is an abelian subgroup of the automorphism group W. And it follows, actually, if you see that this automorphism W1, this is the inner automorphism induced by W1. This lies in the inner automorphism as well as C. So basically, if you put k equal to Ti minus 1 here, so it will reverse this element actually. So it will become W1, Wi, W1. And take all the product of phi k I equal to 1 to n, then it will become the inner automorphism W1. So this makes difficult. This makes difficult in splitting of the natural sort of the sequence of this automorphism group. So anyway, it follows that this automorphism group W is generated by these three subgroups, and it can, the graph automorphism splits over this inner automorphism and C. But the main question here is when does this sort of the sequence split? It is 1 to inner to automorphism to outer automorphism. And here this observation makes the case difficult. And we have a partial result for this splitting of this sequence. Before that, let's see a number theoretic result. So let this M1, M2, and Mn be odd positive integers, each greater than 1. Then the short exact sequence, this short exact sequence splits if and only if there exists a j in between 1 to n and a prime p, which is 3 modulo 4, so that p divides mj. This proof is not difficult. This follows from the fundamental theorem of abelian groups. So this result will help us to decide where the this sort of sequence will split. So with this, we go to the next slide. So this is the final slide. So it follows that this sort of sequence 1 to the inner automorphism by W1 to C, where C was this group, direct product of this C2, C3, Cn, and Ci were this. So it follows that this sort of sequence split if and only if there exists an integer j in between 2 to L and m prime p, so that p is 3 mod 4 and p divides mj. So with this is the final result. If there exists a prime P 3 mod 4, so that P divides Mi for some I in between 2 to L with multiplicity Mi being 1, then the short exact sequence splits. So this is a sufficient condition, not the necessary. And the automorphism W becomes inner automorphism semi-direct D, then semi-direct or comma WS, but D is the complement of the this subgroup generated by the inner automorphism W1 in C. So with this, I'll stop my talk.
Thank you very much, Tushar. Are there any questions for Tushar?
Sir, can you show me the last slide?
Yes.
So, what are the consequences of splitting of these exact sequence?
So consequences means actually we don't know any consequences as of now, but this is a natural question. When one study automorphism, mostly the study the splitting of this sequences. So for that we studied this splitting of the sequences.
Your voice is very low.
Hello, am I audible?
Yeah.
Hello.
I can hear you.
But I am not able to clearly hear you. Maybe I have
Okay, so
my side.
as so there are no consequences, but
Okay.
it is a natural problem when one studies the automorphism group of a group, then they ask the question whether the automorphism group splits over the not automorphism group, and that was the reason behind our study.
Okay.
Splitting.
Okay, thank you.
Any other comments or questions? Let's thank Tushar for a nice talk. Okay. Alexander, you are there?
Yes, can you see me? I think you can.
Yes, yeah, great.
Okay. Give me a second. I'm gonna share the slides.
Yeah, we have a few minutes, so take your time.
Okay. I hope my handwriting is approximately readable. I sort of wrote it like very slowly to offset my general dreadful handwriting, so I hope it's good. Yeah, just tell me when to start and I...
Yes. I will give some very brief introduction and then I will request you to start. I guess since we are all here, maybe it's a good time to start. So our next speaker today is Dr. Alexander Trost from Bochum, and he will be talking about strong boundedness of arithmetic Chevalier groups, a short overview. So over to you, Dr. Trost.
Yeah, thank you for the introduction and the invitation. Yeah, so I'm going to talk about strong boundedness of arithmetic Chevalier groups. What this essentially is the question of how quickly can certain sort of matrix groups defined over rings of integers, or more generally S-algebraic integers, be generated by their conjugacy classes. I'm going to try to be like relatively explicit with the examples I'm going to talk about. It's mostly going to be SLN. I'm going to shortly mention SP4, but for the purposes of this talk, Chevalier group can just mean SLN or defined over some ring of integers. And well, generally, Chevalier groups in general are generalization, or at least to me, they are sort of generalizations of these types of matrix groups. I'm not going to define them completely rigorously, again, because I'm mostly going to sort of focus on this example, but I'm sort of going to at least sort of briefly talk about how one sort of constructs them in completely insufficient detail. So roughly a Chevalier group is G phi R, where phi is sort of a certain type of root system, and R is a ring of commutative integers, is obtained by sort of picking a simply connected, simple linear algebraic group, say defined over the complex numbers, and such that the Lie algebra and the corresponding adjoint action of the sort of say a maximal torus of G on the Lie algebra gives rise to a root system isomorphic to this aforementioned data phi. And then you sort of quote unquote replace the complex entries of the corresponding matrices of the simple linear algebraic group by elements of a ring R. So, it's kind of clear that this is how it works, say, for SLN-R. If you think about the linear algebraic group SLN-Z as the initial data. And yeah, these root systems are sort of classified by multigraphs, which are usually called Duncan diagrams. I'm not going to go into terribly much detail of this, because from some of the previous talks, they got the impression that maybe you kind of already know a lot of this stuff, or at least some of you already do. But for example, for say SL5Z, the corresponding Duncan diagram is this graph where you only have one, what is called root length. It's noted by A4. And then, for example, in this context, GA4 of R is this SL5 of R. And yeah, for the symplectic group, you obtain this Duncan diagram, and this corresponding Chevalier group GCN of R has the symplectic group of rank n, yeah. And then there is the sort of G2 of C, which has this Duncan diagram. And then lastly, we have E6 of Z, which has the Duncan diagram, which I think also makes up the logo of the conference. So I wanted to mention it. And then you have certain sort of important elements in these Chevalier groups called root elements, which are to me generalizations of the elementary matrices in SLN-R. Okay, this is like a bit of the more general framework, and now I'm going to start talking about the conjugation generated word norms that are used to define this concept of strong boundedness that appears in the title. So generally speaking, you pick a group, and you sort of pick some subset of the group that I call T, and then you define this sort of word norm or conjugation generated word norm of T by where you sort of allow the norm of a given element of the group G to be plus infinity as well. As follows. Yes, is there a question? Okay, so where sort of if your group element is some element of the normal subgroup generated by, so these double brackets denote the normal subgroup generated by T to me. So the smallest normal subgroup containing the set T. Then you sort of, okay, so if G is contained in this normal subgroup, you just sort of ask how many conjugates of T or conjugates of T inverse do you need to write this given group element, and you sort of pick the smallest natural number that sort of appears as this number of factors, and just call this the sort of norm of G with respect to T. This is essentially the sort of word norm given by the by the sets of conjugates of T. And if G isn't contained in this normal subgroup, you just set it as plus infinity. And the diameter is kind of defined as one would expect it to be. One just asks what's the maximal possible diameter that can occur with respect to this word norm given by this set of conjugacy classes T, which of course can also be plus infinity on the one hand, because, you know, this group T, the set T might not normally generate the group G you started out with, or it could be plus infinity just because the diameter is just honestly plus infinity, and you can sort of find group elements of bigger and bigger norm with respect to these collection of conjugacy classes. Okay, and this is sort of the norms that we use to define these sort of invariants called delta K of G, which are going to be the main object of study in this talk for arithmetic Chevalier groups. Namely, you sort of ask for sort of a collection of conjugacy classes of T that normally generate a group and that have at most K elements. So, you know, you ask for a collection of at most K conjugacy classes that generate a group, what the sort of maximal possible diameter is with respect to this type of conjugacy classes and this sort of type of word norms. And if there is no such collection of conjugacy classes, set it to minus infinity. This, I did not explicitly mention this here, but these delta Ks form the sort of ascending chain. So delta 1 of G is smaller or equal than delta 2 of G, which is smaller or equal than delta 3 of G, and so on. And the reason to put it as minus infinity if there is no collection of conjugacy classes or below the size of K is just so that this chain of this ascending chain sort of works formally even in this case. And a group is called strongly bounded if all of these delta K of G's are not plus infinity. They do allow that they are minus infinity, but they shouldn't, you know, they shouldn't run off to infinity. And they should, they must, however, they need, however, not be uniformly bounded. So it's, if this is a sort of ascending chain that sort of runs off to plus infinity, that's fine, as long as each single one of them is finite, or not plus infinity. I did not write this here, and I probably should have. I usually refer to these delta K of G's as generalized conjugacy diameters, because they are sort of similar to conjugacy diameters that are studied in the theory of finite simple groups, where you don't need any sort of condition on the group to normally generate, or on a conjugacy class to normally generate a group, because finite simple groups are especially simple. So if you pick a non-trivial conjugacy class, it will generate a group. Okay, so now the sort of type of theorem I'm interested in is, for example, one signified in the following theorem, which is due to Ketra, Liebman, and Martin, at least in sort of spirit. And from 2018, these are my PhD supervisors, by the way. And what the sort of the general shape of these things is that if you pick a ring of algebraic integers and you pick a natural number that is at least 3, then there is a sort of constant Cn of R in the natural numbers, such that you have this sort of upper bound in delta K, which is proportional to K with the proportionality factor given by the Cn of R for all K greater or equal than 1. I should say this is not quite a theorem as it's stated by them. This is more sort of a reformulation or a version of their theorem, which is sort of formulated in a way to be more similar to some of my results. So I'm gonna show the actual theorem by them after I talk about sandwich theorems, which is gonna be making up the third part of this talk. So very roughly speaking, these sort of strong boundedness theorems are proven by showing applying Gödel's compactness theorem to certain types of theorems describing the normal subgroup structure of Chevalier groups. And I'm going to briefly explain how to do this for SLNR so that you have sort of get a general idea of how this is sort of done. For the case of SLNR for n greater than 3, which is sort of in some sense the easiest case, and the more other Chevalier groups have a more complicated the normal subgroup structure is a bit more complicated, but these arguments sort of look similar that prove results like that. Okay, so what are sandwich theorems? First, I have to introduce two types of normal subgroups of SLNR, where now R is for me in the moment a commutative ring, not necessarily of integers, just a commutative ring, which is associative and has the one element 1, and you pick some sort of ideal in this ring, and then you can define sort of two normal subgroups associated to this ideal on the one hand, and here it kind of cut away the second bracket. You look at the normal subgroup of SLNR, which is generated by elementary matrices, such that their arguments sit in this given ideal I, which is a normal subgroup of SLNR. And then secondly, you look at the sort of principal congruent subgroup which you define as the kernel of this sort of reduction isomorphism from SLNR into PSLNRI. I think technically usually one says into SLNRI, but for the purposes of this talk, it's more useful to me to consider the sort of principal congruent subgroup as being the kernel of this map into PSLNRI, simply because sort of scalar matrices are kind of trivial to me as well, and due to the fact that we often play with sort of conjugation and scalar matrices sort of stay invariant under conjugation, it's a bit more sensible to look at this adjoint group here. And now the sort of obvious observation is that this sort of elementary congruent subgroup ENRI is sort of contained in this principal congruent subgroup. Okay, and now the sort of sandwich theorem you use, and I'm sort of give just a couple of names here. There are quite a lot of other people I could reasonably name here. I could, for example, also name Bas, but well, this page is only so long, and I decided to just go with these two. Is that if you have a commutative ring R and you have a natural number which is at least 3 and some normal subgroup of the corresponding SLNR, then there is some ideal I of R such that N is sort of sandwiched between these two normal subgroups, En R of I and Cn R of I, where I, of course, depends on the normal subgroup. And this sort of can be used to derive these strong boundedness theorems, for example, as follows. So if you sort of start out with some element A of the normal subgroup, later or in a second, A will start to be an element of a collection of conjugacy of elements that normally generate a group, but for the moment, A is just some element. Then one can sort of see that if you look at the normal subgroup, which is generated by A in SLNR, then the sort of elementary matrices, or the elementary matrix E1 end of T, where sort of I remind you of the convention. So Eij, elementary matrix, has sort of the only non-trivial entry of the diagonal in the ith row and the jth column, and X just denotes this elementary entry. Then, okay, so now I went a bit too far. Then sort of the fact that this normal subgroup here can be sort of sandwiched between the elementary and the congruent subgroup tells you that the elementary element E1T has to be contained in this elementary subgroup and has to be contained in N of A for the ideal I being given from this theorem. And what's clear is that I will be equal to this sort of level ideal oh, well, it's not immediately clear, but if you think a little bit about this sort of level ideal, which consists of the off-diagonal entries and the sort of differences of diagonal entries, definitely has to be contained in this ideal I, because, well, it does sort of force this this matrix to become scalar after reducing modulo it. Okay, now I lost my train of thought. Yes, so an element T in this level ideal has to be contained in here, and then has to be contained in here. And this sort of implies that A can be written as a sort of product of conjugates of A or A inverse, where the sort of conjugating elements are elements of SLN R. But crucially, all of this is sort of valid for all rings of commutative for all commutative rings. And so this can be this sort of theorem can already, or this sort of conclusion that this elementary matrix is writable as some conjugate can already be derived in the first order theory. And so you can apply Gödel's compactness theorem to obtain, you know, apply to a sort of appropriately written theory of first order of commutative rings to obtain that there is in fact some sort of global bound. Yes, there is some global bound Ln here, which doesn't depend on T and doesn't depend on the sort of initial data of A and the initial ring R, such that this E1T can be written as at most Ln, where Ln is the sort of global bound conjugates of A or A inverse. And sort of in the previous notation of these sort of conjugation generated word norms, this is can sort of be written as that the norm of E1T with respect to this the conjugacy classes given by A is at most Ln. But now if you sort of say, okay, I'm not interested in just sort of any A, but I pick like a collection of conjugacy classes that generate SLN R, and now R is going to be a ring of algebraic integers again, you can sort of see that some of the corresponding level ideals, which are defined as in the previous page, have to add up to the entire ring. Because if they sort of didn't, then the sort of collection T, which is sort of supposed to normally generate SLN R, would not sort of, it could not possibly generate the entire group, because it would be sort of confined to this proper normal subgroup given by the sort of level ideal of T, which is just, well, I should have written LT here instead of I. So this is just a sum here. And well, yeah, that sort of contradicts our assumption. So these sort of level ideas have to add up to the entire ring. But now you can sort of apply this sort of observation star here to the setup and see that, well, each E1T for T some element of A, LAI has norm at most L of N, Ln. And so you get sort of one Ln for each element of T here, within the sort of K elements. So you can sort of see by just sort of applying this, yeah, applying this observation for each AI that sort of all elementary matrices have this upper bound in terms of the cardinality of T. And now you can sort of use Wile group elements to sort of move, or conjugation with Wile group elements to move this elementary matrix about the group SLNR to sort of see that you actually can find all EIJ or all elementary matrix EIJ T in some T-bar of size at most Ln times K, where K is the cardinality of T. And this is sort of, now you sort of combine this with this theorem by Carter and Keller about boundary generation for SLNR, which sort of in a very, very roughly states, to sort of throw away a couple of details, that you can write each element of SLNR, where R has to be a ring of algebraic integers now, as some as a product of, say, Kn of our elementary matrices Eij of T. But now we know how sort of big these elementary matrices are with respect to the norm given by T, and we know that each group element of SL and R can be written as a sort of product of Kn of R many elementary matrices, and combining these two facts together, you get that the diameter of SL and R with respect to T has to be, well, ln times K. This sort of gives us the elementary matrices, and then multiplying further with Kn of R gives us the entire group. So you get this sort of upper bound, which is proportional to K, and now you can sort of, in view of the previous theorem, define this thing here as, I think I called it Cn of R. Yes, yeah, if you define this as Cn of R, then you get this theorem by Ketel, Liebman, and Martin. Okay, so like I said, this is not quite the way they state this. This is also not quite the way they proved this. It's sort of more of a reinterpretation. What they actually showed was way more explicit. They sort of showed that if you start out with a ring of algebraic integers and a number field k and some natural number, which has to be at least 3, then you sort of get this bound on these delta k's. That is sort of morally, this proof that I've just given is the way they sort of provide this upper bound, except that they sort of do it explicitly with matrix calculations and consequently get explicit bounds instead of this sort of abstract compactness argument that I've given here. In particular, the sort of lower bound here states that there is sort of a normally there is a collection T of sort of each size K that normally generates this group. They sort of define this as some collection of elementary matrices with coprime elements, coprime arguments that have a lot of such that the arguments have a lot of common prime factors. And similarly to sort of this theorem by Ketel, Liebman, and Martin, one of the results from my PhD thesis was that this sort of can be generalized to pretty much all split Chevalier groups. If you disregard for the moment the 3 problematic ones, A1, C2, and G2, and then there is some sort of constant L phi of R, which is obtained in a similar manner to this compactness argument that I presented, such that you still have this type of sort of chain of bounds of bounds on delta K of G phi R, where you have upper bounds proportional to K and lower bounds proportional to K. And and in particular, you still have the normal generating sets of each size. If you, however, look at these sort of problematic root systems, C2, G2, and A1, and these are sort of the matrix groups SP4, G2, and SL2, the situation is a little bit different. It's sort of, generally speaking, more complicated, and especially in regards to these lower bounds here. I'm gonna just give briefly an example for SL2 of R, and yeah, then I'm actually kind of done already. So, but there are sort of versions of this theorem that I'm gonna show now for SP4 and G2 as well. So generally, so we pick a ring of algebraic integers. Now we have to assume it has infinitely many units. This is because a lot of these sort of, or that essentially all of these strong boundedness theorems are in some sense versions of bounded generation statements. And well, you don't, well, SL2, which is the group or linear group this which is this theorem is about, of any of say Z is not boundedly generated. So you need a slightly different setup, and you can't just look at all rings of algebraic integers. Okay, so now you have sort of certain types of problematic primes, which, well, one has to count. So for example, I define R1 of R as the number of unramified prime divisors of the rational prime 2, such that the field of residue is set 2. Then you define R2 of R as the number of ramified prime divisors of the rational prime 2 with the field of residue set 2. And I define Q of R as the number of prime ideals or prime divisors of the rational prime 3 with the field of residue Z3. And then you can define the sort of number V of R, which is the maximum of these two expressions here, 2R2 of R plus R1 of R and Q of R. And then you can sort of find a constant LR of N, LR and N, such that if you assume that your K is bigger than the sort of number V of R, you still have these sort of centrage or the sort of chain of of bounds on delta K of SL2R, where you have especially this lower bound of K, especially this tells you that there is a normal generating set of size K for K's bigger than this number here. And you still have this sort of upper bound LR of K, which is proven in a similar manner than the sort of argument I gave for this Kettler-Lippmann-Martin theorem, but the sort of normal subgroup structure of SL2R is more complicated in this case. So it's a little bit more involved. It sort of uses a Sandwich theorem by bad with names, I think Costa and Keller. And yeah, so this is this first part here. And the second part is that delta K of SL2R is minus infinity if your K is sort of smaller than V of R. This V of R is in fact the sort of rank of the abelianization. And if you think about it, if you have a sort of collection of conjugacy classes that generate a group, and then it will map onto a generating set of the abelianization. So if you pick a collection of conjugacy classes which has less elements than the rank of the abelianization, then it cannot possibly generate cannot generate the abelianization, or it cannot map onto a generating set of the abelianization, and it can't be a normal generating set of the initial group. And this is sort of how what goes into the second part, and I'm quickly gonna go through the proof of the second part. The first part is a little bit involved, but the second part I think is kind of nice, so I'm quickly gonna go through that. So you count, so you essentially sort of construct apomorphisms for each of these types, or apomorphisms or quotient maps into abelian groups for each of these types of problematic prime divisors. So you say count Q1 up to QR1 of R as the let them be the unramified prime divisors of the rational prime 2 with field of residue Z2. And you can sort of observe that then you have this sort of, SL2 of R mod QJ, then is of course SL2 of Z2, but there is sort of this exceptional isomorphism to the permutation group on 3 elements, sigma 3. And then you have the sort of epimorphism into Z2 for all of these J's. So yeah, this sort of gives you some quotient map into an abelian group. Then for the sort of ramified prime divisors, you have a sort of slightly different setup. We look at this quotient R mod pi square, where the pi's are these sort of ramified prime divisors. And you look, then you sort of obtain this quotient here, Z2t modulo t square, and you can sort of show that this is sort of isomorphic to the semi-direct product of F2, so Z2 3, and the permutation group sigma 3, where sigma 3 operates by permutation of coordinates on the sort of Z2 vector space, Z2 3. And then you can use this sort of to construct an epimorphism from SL2 R mod pi square into Z2 square, where you sort of map the permutation from sigma 3 to its corresponding signature, and you map the element of Z23 to this to the sum of its arguments. And due to the fact that the permutation operates by permuting these coordinates, and this expression is sort of invariant under permutation of coordinates, this sort of gives you an epimorphism. And yeah, then you also have some epimorphism of this type for the rational prime 3, where you can, for example, use this presentation of SL2 Z3 to see that. Yeah, I don't know. This is just this is relatively straightforward. I think the more surprising thing here is the one coming from the ramified prime divisors, and then sort of if you stick all of these problematic primes together, you get an epimorphism from SL2 of R into, well, this giant quotient of R. And then you can sort of apply the Chinese remainder theorem here to pull these things apart. And then you sort of use these epimorphisms for the various primes that I mentioned now to obtain this abelian quotient H here. And well, yeah, then you sort of use this argument I sketched before, that if you have a collection of conjugacy classes which generates SO2 of R, then it will automatically map to a generating set here, and hence it cannot be smaller than the rank of this.
Last 2 minutes, Alexander.
Yeah, I'm almost done. Like the next page is the last one. Then the sort of yeah, then it maps onto a generating set, and the rank of this sort of abelian group is in fact this maximum here. And yeah, this sort of proves this second part here. And for SP4 and G2, the situation is quite similar. This is sort of contained in a previous preprint of mine, but it's overall easier. So for example, you don't have this distinction between ramified and unramified prime divisors of the rational prime 2, but just the sort of sum of R1 and R2 is the sort of abstraction to small normal generating sets here. And well, 3 is not a problematic prime for us. Well, it kind of is for G2, but it's not problematic enough, if you will. And yeah, I think this actually kind of concludes my talk already. So yeah, thank you for your attention.
Thanks a lot. Let's thank Alexander. Are there questions or comments?
Yeah, I have a question. Maybe I lost focus after some time, but you mentioned this upper bound L phi R for a root system phi and ring of integer R.
Yes.
So do you know if this is always a polynomial kind of thing in the rank of the group?
Yes, it definitely is a polynomial. The question is more what kind of polynomial it is. That's actually kind of the question I'm currently working on.
I see. Oh, thank you.
Yeah, I didn't mention this, but this lower bound here actually can be improved to the rank of phi times k.
I see. And the ring of integer, how much role does it play in this determination of this bound?
Well, that's also a kind of a good question. If this thing has infinitely many units, it doesn't seem to be all that relevant what ring you actually pick, because there is this quite neat theorem by Rapinchuk, Morgan, and Zuri, and it states that you have sort of bounded generation pretty much completely independent of any invariance of the ring of integers for in this case, and you can sort of pull this up to get good bounds here that don't depend on the ring all that much. If it depends on, or if it's not, if it's the ring of integers or the ring of imaginary quadratic integers, it seems to be a bit unclear. At least it's unclear to me. I kind of think that it shouldn't depend on it either, but that's just a wild guess on my part. It might also be wrong what I just said.
So ideally, you would say that it doesn't depend on the ring of integers.
Yeah, that would be my dream. Yeah, I should, however, mention in this context, if you and write this down, but if you do this thing for SP4, so delta k of SP4, you will have these sort of minus infinity issues down here, where you don't have normal generating sets, but you actually sort of see this sort of number of problematic primes pop up in the bounds. And I think then the sort of better question would be, okay, I'm actually amending my previous answer. In this case, it depends, but I do think that if you sort of pick like bigger and bigger conjugacy classes or collections of conjugacy classes, it shouldn't depend like in the limit. In the limit, these sort of dependencies on the number theory should vanish.
Right.
Okay, sorry. Yeah.
Are there any other questions? I have a question here. So here you were looking at this set T and you are collecting all conjugates of T and then looking at the group generated by that.
Yeah.
So is there some finiteness result that may be known? So for instance, if you're looking at elementary matrices, do we know that there are finitely many conjugates of the subgroup that will be enough. To give you a context, if you're looking at these split groups over a field, then there is Gruha decomposition, which will tell you that essentially finitely many one-dimensional groups, subgroups will generate the whole group. So that was the thing I was looking at. So your elementary subgroups are one-dimensional, sort of.
Yeah.
And you are taking all their conjugates. I was wondering if finitely many conjugates of them would suffice. Would you know of any such thing?
Not on top of my head. There is this. No, so the honest answer is no. I could say a little bit about a paper by Liebeck, but no, I don't actually know in the ring case.
Which paper of Liebeck?
There is a paper by Liebeck and Shalev where they sort of do this conjugacy diameter thing for finite groups of Lie type, and you could sort of recast certain things that they do there in terms of the Pura decomposition, but
okay.
that's for the field case, and for the ring case, it's not clear to me, to be honest.
Okay.
There is a sort of result mentioned, I think, that Steinberg mentions in his lecture notes in Chevalier groups for principal ideal domains, which is sort of a flavor of a Pura decomposition thing. And I do use this to give some bounds in my thesis, but ultimately for like the general ring case, I just don't know, to be honest.
Okay. All right, let's thank Alexander once again for a very nice talk.
Thank you for having me.
So if you could stop sharing, Alexander. Yeah.
Yes, I will.
Ashish, are you ready?
Yeah, I will share my screen. Just a second.
Sure. Meanwhile, while Ashish shares his screen, I would like to make a small announcement that tomorrow at the end of all talks at 5:30 p.m., we would request all the participants to be present and start their video. We would like to take a group photo of the whole conference. Okay, so our last speaker today is Dr. Ashish Mishra. He is also a student from my institute, IIT Bombay. He finished his PhD with Professor Murali Srinivasan, and he is at Brazil at present. He is going to speak on a Sangam of spectral approach and sure-while duality, a very interesting title. Over to you, Ashish.
Okay, thank you, Shripad. At the start, I would like to thank Professor Anupam Singh and Professor Manoj Yadav for planning this semester-long seminar series. I mean, it was very useful personally to me, and also I had interaction with many Indian mathematicians after a long time. Okay, and okay, so when I wrote the abstract for this talk, the title at the starting was different, but then I thought to change it to this title, A Sangam of a Spectral Approach and Sure-while Duality, based on the theme of the name of the conference. Okay. I would also like to thank organizers of the conference for giving me this opportunity to talk about this work. The results which I present here are mainly parts of the research projects with Dr. Shraddha Srivastava. So let us start. As the title shows, that we will study an interaction between spectral approach and sure-while duality. So let's start with general linear Lie algebras. We can consider their chain. GL1 is contained inside GL2 and so on. GLN minus 1 is contained inside GLN in a natural way. Okay. And it is well known that this chain is multiplicity free. What do I mean when I say that this chain is multiplicity free? That if we take a representation of GLN and restrict it to the representation of GL to be a representation of GLN minus 1, then the representations of GLN minus 1 which appear in this decomposition appear at most once. Okay. So corresponding to this multiplicity free chain, we get a basis of GLN, and highest weight theory is well known. In the highest weight theory for the representation theory of complex semi-simple Lie algebras. Of course, GLN is not semi-simple, but yeah, it is almost. So these basis vectors of the irreducible representations of GLN. Because of this chain, this multiplicity free chain can be parameterized by a combinatorial object, which is known as standard Gelfand-Zeppelin tableaus of height n. Okay, and of course, given any Lie algebra, we can define the universal enveloping algebra of this Lie algebra. So corresponding to this chain, we have a chain of universal enveloping algebra also, and to each UGLM, we consider its center, and we consider the centers of UG1, UGL1, UGL2 up till UGLN, and consider the subalgebra generated by these centers. And this subalgebra is known as Gelfand-Zeppelin subalgebra. This Gelfand-Zeppelin subalgebra plays an important role in the representation theory of general linear Lie algebras. Okay. Now, a generalization to the infinite dimensional representations. This work was done for finite dimensional representations. This was done by Gelfand and Zeppelin in 1950s, and later on there have been many attempts for infinite dimensional representations. For example, by Gelfand, Grieve, Mazurchuk, Molev, and recently in 2019 there is a paper by Slava Futorny, Ramirez, and Zhang on combinatorial construction of Gelfand-Zeppelin modules for GLM. Okay. That is about the case of Lie algebras, from where the original motivation and idea for spectral approach comes. Okay, now consider a multiplicity-free chain of finite dimensional semi-simple algebras. The multiplicity-free chain means the same thing, that if I take an irreducible representation of AH and consider it as a representation of AH minus 1, then it decomposes into a direct sum of irreducible representations of AH minus 1 with each irreducible representation appearing at most once. Okay. Now, since in the decomposition isotypical components are canonical and every irreducible representation here appears at most once, so this decomposition is into irreducible representations is canonical. And if we go on doing this recursively from AH to AH minus 1, then to AH minus 2, and so on, we get a canonical basis, which is called Gelfand-Zeppelin basis of an irreducible representation of AH. And there are some special elements which are known as UC Murphy elements. These are in the algebra AH, which play a central role in the spectral approach. Why is it called spectral approach? We will see in the next slide. But what are the advantages of the spectral approach? One advantage, and the first important advantage, is that this considers the representation theory of the whole family rather than considering an individual object. Secondly, usually we get some kind of combinatorial object which parameterizes the irreducible representations and their bases. For example, in the case of symmetric groups, Young diagrams parameterized by irreducible representation and their bases are parameterized by standard Young tableaus. Okay, and spectral approach is important in itself, but there are some new applications also. Like Murli has a paper on the decomposition of Boolean algebra as a permutation module of symmetric group, and in my thesis we had done the decomposition of generalized Boolean algebra as a permutation module of Reed product. And recently Shubhajit Ghosh, who is currently a postdoc at IIT Bombay, has studied properties of random walks on Reed products of finite groups by symmetric groups using this spectral approach. And these UC Murphy elements play important role there in his work. So what are the important properties or fundamental properties of UC Murphy elements? There is no known algorithm to determine UC Murphy elements. So we search for the elements which satisfy these properties and we call them UC Murphy elements. So the first property is these elements commute with each other. Okay. They are not central elements. Second property is that the irreducible representations of AH and their bases are determined by the actions of these elements. What I mean here is that these elements act as scalars. on these irreducible representations, and these scalars actually determine the irreducible representations, and therefore this approach is called spectral approach. And of course, we are considering a whole family, a chain of a multiplicity free chain. So this can also be called inductive approach. Okay, and UC Murphy elements are usually, a UC Murphy element is given by the difference of a central element in AH and a central element in AH minus 1. So if you sum all the UC Murphy elements of AH, it becomes a central element of AH. So some families of groups and algebras for which the spectral approach has been done are, symmetric groups. Of course, this was the first one here. It was the first paper appeared in 1996, and a more refined version appeared in 2005 by Okonkov and Vershik. And spectral approach in the context of symmetric groups is also known as Okonkov-Vershik approach. For partition algebras, it was done by Halvorsen and Ram in 2005. For Q-root monoid algebras, it was done by Halvorsen in 2004. For reproduct of finite groups by symmetric groups, it was done by myself and Murli Srinivasan. And in this talk, I will mainly focus on partition algebras for complex reflection groups, which was done by myself and Shraddha Srivastava. And recently, we have also done spectral approach for root monoid algebras and for partition algebras for root monoid algebras. And also last month, there was a paper on arXiv by Mazharchuk and Shraddha Srivastava, which deals with the spectral approach on generalized root monoid algebras. Okay. So now let us see complex reflection groups. Let me first define the group GRPN, and then we will come to the complex reflection groups. So R, P, M, and N for us are positive integers such that P divides R. It is important to note that, many times we subconsciously think that P is a prime number, but that is not the case here. P is any positive integer which divides R, and M is equal to R by P. So one can think about the group GRPN in many ways. One of the ways is to think that GRPN is a subgroup of GLNC, which consists of n by n generalized permutation matrices with non-zero entries being RF proofs of unity, and the mth power of the product of non-zero entries is 1. For example, for the case when P is equal to 1, this GR1n is the Reeve product of cyclic group of order R by symmetric group on n letters. Okay, and GRPN is an index P subgroup of index P normal subgroup of GR1n, and this plays a crucial role. Also, the quotient group GR1n by GRPN is a cyclic group of order P. So these things are important in the context of Clifford theory, which we use to determine the irreducible representations of GRPN. Okay. By V, I mean it was already known. I'm not saying that we did it. So now let us come to Shepard-Todd classification. Okay, in the case of complex simple Lie algebras, it is well known that there are 4 infinite families of complex simple Lie algebras, which are A and B and C and D n, and there are 5 exceptional cases. In the case of complex reflection groups, by Shepard-Todd classification, there are 37 different types of finite irreducible complex reflection groups, out of which there are 3 families which are infinite, and there are 34 spatial cases. Okay. So let me first define what is a complex reflection group. A reflection on a finite dimensional vector space is a linear isomorphism of finite order, which fixes a hyperplane of codimension 1. That means that its n-1 eigenvalues are 1. Okay. Usually this is called pseudo reflection in literature, but we started learning this subject from the works of Shepard-Todd and from the paper of Cohen, and both of them call this as reflection. So we continue calling it as reflection. Okay, and so this is the definition of a complex reflection group. What is an irreducible complex reflection group? Sorry, this is the definition of a reflection. A complex reflection group is generated by reflections on a vector space, and an irreducible complex reflection group or a complex reflection group is irreducible if the complement of the G invariant subspace of this reflection representation is also irreducible. Okay? And it is a theorem by Shepard and Todd that GRPN is the only infinite family of irreducible finite complex reflection groups. The only exceptional case here is when RPN is 222, that is not irreducible. And also, there are some well-known families which are complex reflection groups. One is symmetric group, and of course, cyclic group of order R, while group of type Bn, Dn. Dihedral groups are complex reflection groups. Also, there is a theorem by, the theorem is known as Chevalier-Shepard-Todd theorem, that the ring of invariance of the action of a finite group on a complex vector space is a polynomial ring if and only if it is generated by pseudo reflections, which means that it is a if and only if it is a complex reflection group. Okay, and today we also had a talk by Tushar, where he was talking about Coxeter groups, which are also reflection groups. So in this context, the complex reflection groups are important, and GRPN being the only infinite family is important to study. Okay, so now let us come to the representation theory of GRPN. It is well known that the R tuple of Young diagrams with total number of boxes n, with total number of n boxes, parameterizes the irreducible representations of GR1n. Okay, and then we use Clifford theory to determine the irreducible representations of GRPN. So take this R tuple lambda 1, lambda 2, lambda r, then for each I between 1 and n, you make a jump of n, lambda I to lambda m plus I to lambda 2m plus I, and so on till lambda p minus 1 times m plus I, and draw this as a necklace. Okay, this is called the ith necklace, denoted by lambda tilde I. And then we have this m tuple of necklaces, lambda tilde 1 till lambda tilde n, and this is called an MP necklace. Now this this group ZP has a natural action on these necklaces, and C lambda, let C lambda denote the stabilizer subgroup of ZP with respect to this MP necklace lambda tilde. Okay, and this is a theorem by Stenbridge. I mean, we first saw it in a Stenbridge, so I'm calling it by a theorem by Stenbridge. He uses Clifford theory to show that the irreducible GRPN modules are parameterized by the ordered pairs, this MP necklace, and this delta an element of the stabilizer subgroup. Okay, and this fits well when P is 1, because this delta is anyway 1 in that case, and these MP necklaces will turn out to be, in that case, when P is 1, this is just R tuple of Young diagrams with total number of boxes n. So let me come to partition monoids. Partition monoids, partition algebras were defined independently by Jones and Martin. These were defined as a generalization of temporally algebras and Potts model in higher dimensional statistical mechanics. There was a talk in the seminar series by Geeta on partition algebras, on diagram algebras. So this k is a non-negative integer. Ak is the set of all set partitions of 1 up to k, 1 prime up to k prime. These elements of AK can be depicted as graphs, which are called partition diagrams. And AK is a monoid with the multiplication, which is obtained by concatenation of the corresponding partition diagrams. Okay, this monoid is called partition monoid. Okay. An example is on the next slide, but I will skip it at the moment. Okay. And partition algebras, for any Q, a complex number, the vector space CAKQ is the C span of these partition diagrams, and the multiplication is defined as D1, D2, which is Q raised to power L, D1 circle D2. Here, this L counts the number of blocks which have been removed from the middle while computing this D1 circle D2. The algebra CAKQ is called the partition algebra. Okay. Now we come to Schur-Weil duality. consider the n-dimensional complex vector space B. And in classical Schur-Weil duality, we study the action of GLNC and SK on V tensor K. Here this Sn is a subgroup of GLNC and it acts on V tensor K in that way. I mean, by the restriction of the action of GLNC on V tensor K. And we can give an action of CAKN on V tensor K, and these are in Schur-Weil duality. What we mean by this is that these two actions commute with each other, and these two actions generate the full centralizer of each other. And the representation theory of one can be studied by using the representation theory of other. Okay. This was defined by Jones and Martin independently. And the next question is, symmetric groups are a particular family of complex reflection groups. So what is the partition algebra for the complex reflection groups? So what was already known, there is a paper in 1997 by Tanabe on the centralizer algebra of the unitary reflection groups, where he studies this topic. And later on in 2007, there is a paper by Orellana on partition algebras for complex reflection groups, which appeared in Journal of Algebra. Here, she studied the partition algebra for GR1n, so for P is equal to 1 case. And also, she did not study the spectral approach. She does not have U-symmetry elements and their actions. And there are many other results which are missing there, even for the P is equal to 1 case. So this is our paper, which appeared in Algebraic Combinatorics, which is titled On Representation Theory of Partition Algebras for Complex Reflection Groups. Here we study, we define partition algebras for complex reflection groups for any P. Okay, so this was the first problem, that for defining the partition algebras. In Orellana's paper, she uses she uses diagram basis to define partition algebra for GR1n case, and it can, and actually diagram basis is not very helpful here. It is actually another kind of basis, which is orbit basis, which is more helpful here in the general P case. Okay, and we use that to define partition algebra for complex reflection groups. And it can be shown that in P is equal to 1 case, both the algebras turn out to be same. Okay. And the proof that it is an algebra, so one has to define the multiplication using orbit basis and the structure constants. So we call this algebra Tanabe algebra, and you can see the definition later if there is an interest. Okay. Then we prove that this algebra, Tanabe algebra TKRPN, is in Schur-Weil duality with GRPN while acting on V tensor K, which means that the actions commute with each other, they generate the full centralizers of each other. And the representation theory of one can be studied using the representation theory of other. Okay. Anyway, in Schur-Weil duality, I mean, the problem is on both sides here, on the side of TKRPN also and on the side of GRPN also. Okay. If one was known, the other would be known. So the first thing was to define this TKRPN, and then there to explain this, I mean, Sn minus 1 is a subgroup of Sn, the set of all elements which fixes them, and this restriction is multiplicity free. In partition algebra, this chain plays an important role. So correspondingly, there needs to be a subgroup here which plays the analogous role of Sn minus 1 here. So I have not defined it here. That group we denote by LRPN. And one has to study the restriction rule from GRPN to LRPN. For that, we need to construct a basis of irreducible GRPN modules. And this uses a confluence of ideas from different approaches, one from Akungo-Vershik approach, Clifford theory, and higher spec polynomials. And then we apply this to determine the branching rule. So the next important result is the decomposition of the centralizer algebra into irreducible modules. These are parameter. And then the next result is parametrization of the irreducible modules of Tanabe algebras. These are parametrized by the same. Okay. MP necklaces, and delta, where delta is an element of C lambda. And corresponding to LRPN, we have half Tanabe algebras with the irreducible representations of which are parameterized by Nij colored MP necklaces. Okay. Then we construct Bernoulli diagram. Bernoulli diagram just recursively constructs the restriction from AH to H minus 1 to H minus 2 and so on. And it is shown that this Bernoulli diagram is a simple graph. Finally, we give the description of UC Murphy elements of Tanabe algebras and their actions on a canonical basis called Gelfand-Zeppelin basis of each irreducible module of Tanabe algebras. Actually, there is an online notes by, online notes by Arun Ram, where he has written these UC Murphy elements, and these turn out to be the same except in the special case when RPN is 2K. Okay, so these are all the important results. So with this, I finished my talk, and I thank everyone for their attention.
Thank you, Ashish.
Thank you.
Are there any questions or comments?
Should I stop sharing or?
No, let it be.
Okay. Hello.
Yeah.
Yeah.
Okay, so since there are no questions or comments, let's thank again Ashish for his nice talk.
Thank you.
Yeah. There is a announcement once again that tomorrow around similar time we will have a group photo. So please be present, and we will request you to start your cameras. I think now people can discuss. There will be breakout rooms, and now the floor is open to everyone. Thanks a lot to all speakers today and to Amit Kulsresh for the technical support.